Hi everyone. I hope you have already gone through my first lecture on fundamentals of radiation heat transfer. With that understanding, today we will try to solve a few problems. First problem says, assuming the sun to be a black body emitting radiations with maximum intensity at lambda equal to 0.5 microns, calculate the surface temperature and emissive power. So what is given in the problem? First thing is, you can assume the sun to be a black body. So you can use all the formulae applicable for a black body. Then it says its maximum intensity of radiation occurs at 0.5 microns. That means lambda max is equal to 0.5 microns. To convert that into meter, multiply it by 10 power minus 6. We have to calculate its temperature and emissive power E suffix B. So by using Wien's displacement law, lambda max into T is equal to 2898 micrometers. Lambda max is given and 2898, no, it is the constant. You just multiply it by 10 power minus 6 to make it into meter Kelvin. This is not simply Kelvin, this is meter Kelvin, right? From this you can calculate temperature to be 5796 Kelvin. So this is the temperature of the sun. Second thing is to calculate the emissive power. You know, as per Stefan-Boltzmann law, emissive power of a black body EB is equal to sigma into T power 4. Sigma is Stefan-Boltzmann constant, you know already, it is 5.67 into 10 power minus 8 watts per meter square Kelvin power 4 multiplied by temperature of the sun in Kelvin scale raised to the power 4. So you will get emissive power as 63.988 in 10 power 6 watts per meter square. Hope you understood. It's a very simple problem only. Now we'll try to solve the second problem. It says a black body at 3000 Kelvin emits radiation. Calculate the following: monochromatic emissive power at 1 micron wavelength, wavelength at which emission is maximum, maximum emissive power, total emissive power, and then emissive power of a real surface at an emissivity of 0.85. So what is given in the problem? First thing is, it is a black body. You can assume it to be a black body and calculate everything. We have to calculate monochromatic emissive power, that is EB lambda at a lambda of 1 micron we have to calculate. Then wavelength at which the emission is maximum, that is lambda max we have to calculate, and maximum emissive power, that is emissive power, the corresponding lambda max, then total emissive power EB. So all these four subdivisions we can solve assuming the body to be a black body. The fifth subdivision is different. It says there is a real body having an emissivity of 0.5 and we have to calculate the emissive power of that real body actually. So you have to use the formula for real body for solving the fifth subdivision, right? So to say, what is given? Temperature of the black body is given as 3000 Kelvin. We have to calculate monochromatic emissive power at lambda of 1 micron, that is 1 to 10 power minus 6 meters. And for the fifth subdivision, they given the emissivity of the real surfaces 0.85. Okay, yes. So these are the things we have to calculate. Monochromatic emissive power EB lambda at lambda equal 1 microns, lambda max, EB lambda max, then total emissive power EB, and finally emissive power of the real surface. Small correction, this you can take it as E, not EB real, simply E real you can say. So monochromatic emissive power is a formula as per Planck's law. We know already. EB lambda is equal to C1 into lambda power minus 5 divided by e power C2 by lambda t minus 1. C1 and C2 are constants whose values we can read from heat transfer data book. Right. So substitute the value of C1. Lambda is given as 1 micron, that is 1 in 10 power minus 6 meters or minus 5. Then the denominator e power C2 constant, and the lambda is 1 in 10 power minus 6 and t is 3000. So if we simplify, we will get EB lambda, that is monochromatic emissive power at lambda equal to 1 micron is 3.1178 into 10 power 12 watts per meter square. Clear? Then we will proceed to calculate lambda max. As we already used the same thing in the first problem. So as per Wien's displacement law, lambda max and T equal to 2898 micron Kelvin, and if you multiply it by 10 power minus 6, it becomes meter Kelvin. So temperature T is given. We can calculate lambda max to be 9.66 into 10 power minus 7 meters. That means this body is emitting maximum radiations at a wavelength of 9.66 in 10 power minus 7 meters. So then to calculate maximum emissive power, the formula for calculating maximum monochromatic emissive power EB lambda max is equal to C4 into e power 5, where C4 is a constant whose value is 1.307 in 10 power minus 5 and temperature is 3000. Substitute, you can find out maximum emissive power to be 3.176 into 10 power 12 watts per meter square. Okay. Then total emissive power or simply emissive power, that is EB is equal to sigma and T power 4. You know what is sigma. Substitute the value of temperature as 3000. We'll get EB total emissive power to be 4592700 watts per meter square. Finally, the fifth subdivision, emissive power of a real surface. You know, emissivity is defined as the ratio of emissive power of a given body to the emissive power of a black body. So emissive power of a real body can be calculated as epsilon multiplied by emissive power of a black body, which we have discussed in the first lecture. So using that, here sigma in T power 4 represents the emissive power of a black body. We just multiply it by the emissivity of the given real surface, we will get emissive power of the real surface. So epsilon is given as 0.85 in the present problem, and sigma in T power 4 comes to be 4592700, right? So finally we will get emissive power of the real surface as 3903795 watts per meter square. Clear? Hope you understood this. If you have any doubts, please mail me. In my next lecture, we'll try to solve few more problems.